Hello and welcome to your preview of Training to Go modules presented by Technical Sales and Consulting. This preview covers transmission and distribution. It is extracted from our Power Management course. At the end, we will provide how to access more information about our training products. Thanks for visiting and we hope you enjoyed the preview. For more information visit our website trainingtogo.net. It needs to be generated and distributed. Having an understanding of this process is essential to the power management process. Electrical power used in residential, commercial, and industrial buildings is mostly generated by the utility at a central point and transmitted and distributed to where it is required through the utility power transmission and distribution system. The electricity is generated from these sources: coal 33%, natural gas 33%, nuclear 19.5%, almost 8% from non-hydro renewables like wind or solar, 6% from hydro and less than 1% from oil. Let's examine this illustration to get an idea of a transmission and distribution system. T&D for short. A utility power transmission and distribution system controls, protects, transforms, and regulates electrical power so it can be safely delivered to the user. The utility power transmission and distribution system begins at the point of power production and normally ends at a building metered service entrance point, which is where the building distribution system begins. Perhaps stepping through this diagram will be helpful. Later we will zoom in closer to the key areas. The electricity journey starts at the generating station. We previously mentioned the various sources used to generate power. At the station a step-up transformer is used as seen here. After stepping up the voltage, power is then sent through transmission lines. Now what is a transmission line? A transmission line is an aerial conductor that carries large amounts of electrical power at high voltages over long distances. You might hear engineers refer to these as high-tension lines. The transmission voltage level is determined by the required transmission distance as well as the amount of power carried. A larger transmission voltage is chosen when dealing with longer distances or larger transmitted power levels. As you can see, these voltages have a wide range. Why such a high level? Well, one of the basic principles of electricity is that the higher the voltage the lower the current. By lowering the current, greater distances can be maintained with less losses and the size of the current carrying conductors can be reduced, thus providing a great savings. At this point of the journey there may be a large industrial facility with a high electricity demand, such as a manufacturing plant, chemical processing facility, or a large data center, that purchases power at 138 or 230 kV. As the transmission lines continue to move the power, they can connect to a substation which utilizes a step-down transformer highlighted here to drop the voltage as required by the customer and sent over distribution lines highlighted in green here. These voltages include 26 and 69 kV for the sub-transmission customer, 4 and 13 kV for what is considered a primary customer, and 120 and 240 volts for the secondary customer. From this point the power is distributed as needed through these facilities. Distribution substations provide a convenient place along the distribution system for maintenance, checkpoints, and power line adjustments. Let's take an in-depth view of a typical distribution substation. One of the best images is provided by the OSHA website. It shows the power flow through the substation and the various pieces of equipment needed. Coming up we will touch on each piece of equipment. First you see the incoming sub-transmission lines. In this case the incoming voltage is 34 kV. In conjunction with the incoming line you will see lightning arresters. The feed then flows to air brake switches used to isolate for service the equipment in the yard. These can also be vacuum switches and can also be enclosed in the transformer. Next in this illustration you will see oil circuit breakers. Oil circuit breakers are old technology but still exist in some older substations. Today the breakers of choice are vacuum and SF6. There are also some substations with outdoor enclosed air breakers. Next is the step-down transformer. Transforming from 34 kV to a more utilization voltage of 7.2 kV. This usually uses oil for cooling and insulation. This oil in today's transformers is an environmentally friendly, non-toxic fluid called FR3. The secondary of the transformer feeds voltage regulators which in turn are connected to medium voltage metal-clad switchgear. The switchgear contains feeder breakers. The number of breakers depends on the load capacity and the needs for distribution feeds. The load side of these breakers are connected to a bus configuration and fused cutout switches on a rack assembly. It is from here that the power is connected to the outgoing distribution line poles. Coming up, we examine these components in more detail. You never know when lightning can strike. It is a good idea to take the necessary protection measures before it happens. When designing substations, it is essential to install lightning arresters. Here you see lightning arresters installed on the primary side of a substation transformer. These also can be installed on an overhead rack on the load side of the incoming line disconnect as was pictured on the previous slide. Lightning arresters work to suppress surges and lightning by using MOVs or metal oxide varistors similar to those found in the surge suppressors in your home, except they are much larger and heavier duty to allow for absorption and dissipation. There are 3 types of lightning arresters, each for application is their own specific voltage range. Distribution class, which as the name indicates are suitable for use in distribution substations. These are rated 2.4 to 46 kV. Intermediate classes are also available and can be used in distribution substations. These are available from 2.4 to 138 kV. The highest rated lightning arrestor is the station class. These are designed to be used at the generating station but can also be used in distribution substations. These are available from 2.4 kV to 230 kV. As you increase in the class selected, the better lightning protection is achieved. As an example, let's assume this distribution substation was an incoming voltage of 34.5 kV. You could opt for station class arresters. Sometimes design engineers opt to place the arresters on the substation transformer. If that is the case, distribution arresters on the 13.8 kV secondary would be selected. It is necessary to isolate the circuit breakers, transformers and other equipment. One option is to use an air brake switch manufactured by Southern States seen here. This is a single pole but can be grouped with 2 other units for the required 3 poles. These are non-fused and can be operated with a manual crank seen here or with a motor operator seen here. The 3-pole group operated switch and mechanism is seen here. If properly maintained, distribution substation breakers have a very long life. You may encounter some older ones that use an OCBs or oil circuit breaker. This is typical of one. At first glance you can tell that these are vintage and dated, however the design is sound and works well. The tank arrangements and control panel may have different orientations. These are located before the substation transformer and provide the feed to the primary side of the transformer by round busbar. This diagram shows the configuration. Let's zoom in. The external bushings allow for the conductor to be connected. These penetrate the tank and connect to the fixed and moving contacts. The oil in the breaker tank insulates the current carrying parts and also cools the contacts to prevent overheating. When the breaker is interrupted, the arc energy is absorbed by the oil. In addition, the oil reduces wear and tear and prevents oxidation. Another old-school device would be an air circuit breaker or ACB. When you see them in a substation yard, they look huge, almost the size of a large shed. They need to be that way in order to house the arc chutes used to extinguish the arc during interruption. This photo shows the breaker out of the weatherproof house. The arc chutes are located here. This illustration depicts how the arc is extinguished with an air circuit breaker. The image on the left shows the breaker contact closed. When it is opened or interrupts a fault, the arc is moved by the arcing contacts toward the arc chute. The arc chute consists of stacked plates with a gap in between. The arc is then spread out across the plates until extinguished. Coming up, we will look at 2 other options for substations, including air, vacuum, and SF6 breakers. Earlier we spent some time identifying the various types of medium voltage switchgear breakers. It is now time to take a closer look at these breaker elements. Let's start with the air breaker. Based on today's standards, air breakers represent old technology. They are a lot larger than the current design units and therefore need larger enclosures that require more floor space. In addition, these breakers could not be stacked. They utilize large arc chutes to extinguish the arc when called upon to interrupt the circuit. Another big concern was the ionized gases emitted during an interruption. In most cases, these gases needed to be vented through air chambers within the switchgear enclosure and out the top away from personnel. Lastly, these were high-maintenance items requiring inspection, cleaning, and replacing the contacts. Included in this class of breakers are the Westinghouse DHP, the Siemens Allis-Chalmers Ruptair, the GE Magnablast, the Brownbow Vari Type HK, and Square D Solinarc. Newly constructed substations are designed with more updated circuit breakers. First is the vacuum. Vacuum technology allows for higher interrupting ratings as well as a more efficient way to handle the arc, and as you see in this photo, alongside an air breaker it can be installed in a reduced size footprint. Here is the construction of the heart of the breaker, the vacuum bottle. Another popular option is to have a SF6 breaker as seen here. This breaker uses SF6 gas to extinguish any arc. As you can see from the photo, these become quite large. The terminations are made on the line side bushings and usually round bus bars connect to the transformer primary. Upcoming we will examine these breakers in more detail. Vacuum breakers are readily recognized by the distinct bottle or tube-like interrupter when facing the rear of the breaker. Much like the predecessor air circuit breaker, it has primary contacts that connect to the main and load bus. The secondary contacts located here plug into a matching secondary contact block in the switchgear cubicle. This is the vacuum interrupter itself. Depending on the rating, these come in many different sizes. Pole insulators support the bottle for integrity and isolation during operation. Phase barriers are used to isolate the individual power poles. Here is a closer view of a vacuum bottle removed from the assembly. How does vacuum technology work? The bottle consists of two primary contacts enclosed in a vacuum-type envelope made of ceramic material. Each end is sealed with a metal end cap and end shield. Inside the envelope are two contacts, sometimes called electrodes, one fixed and one movable. The movable electrode travels through a bellows connection, which is covered by a shield. When the contacts are separated, the arc is supported by ionized vapor derived from the contacts themselves rather than by ionized gas. Although the physics are complex, the interrupter works because the arc does not have a conducting path and cannot be sustained in a vacuum. New spiral-shaped contacts provide a self-induced magnetic effect that moves the arc around in a circular fashion, which minimizes the contact erosion. Here is a diagram of the SF6 puffer design. Let's go over the components. There are upper and lower high voltage terminal connections. The upper conductor is fixed and the lower conductor is movable. The main current carrying parts and arcing contacts perform the interrupting process. Valves are required to regulate the gas. These are the self-blast, refill, and pressure relief valves. The self-blast and puffer volume are the two arc assist interrupters. The blast volume is thermal and the puffer volume is the compression volume. The nozzle helps with the arc quenching. The operating rod assists with moving the lower conductor. Here is the basic operation. During the interruption, a piston compresses the SF6 gas in a cylinder, all of which is enclosed in an epoxy tube vessel. After the main current carrying contacts part, the current transfers to the arcing contacts. Once the arcing contacts part, the SF6 gas in the compression chamber blasts the arc through the nozzle. The heat created by the arc breaks the SF6 molecules into fluorine and sulfur. Arc energy is absorbed and the arc is cooled. As current zero is approached, the heat energy subsides as more SF6 gas enters the system. At current zero, the high-pressure SF6 gas flows through the nozzle and extinguishes the arc. For all this to take place requires a great deal of mechanical energy compared to that of a vacuum breaker. In addition, the gas enclosure has more parts. The risk for gas leakage is also problematic. Proponents of gas technology, however, tout much less chop occurs during the interruption process. Engineers must take these trade-offs into consideration when designing medium-voltage switchgear. Continuing our tour of a distribution substation, our next stop is the distribution transformer. As seen in this overhead view, the transformers are usually connected with primary bushings on the top by a round busbar on from the load side of the circuit breaker. These transformers are liquid-filled with environmentally friendly FR3 insulating liquid. The voltage is stepped down here to 13.8 kV or 7.2 kV. The secondary is connected to medium-voltage switchgear. These can be breakers or fuse disconnects. They can be connected close-coupled to the transformer with side-mounted bushings with a standard 4-hole pad or by overhead busbar off the top-mounted secondary bushings. These are equipped with tap changers to adjust the voltage, liquid level gauges, temperature gauges, relief valves, and sometimes a sudden pressure relay to help protect the transformer. Manufacturers like Eaton can supply a vacuum breaker within the tank frame, reducing the footprint required for equipment as well as eliminate the need for a busbar that would normally go between the load side of the breaker to the primary bushings of the transformer. This provides a lower installation cost. We mentioned a tap changer is included on substation transformers. Here is an explanation of how taps can be changed. The source voltage can be higher or lower when supplied by the utility. Taps allow for application flexibility and allow the user to change the primary winding to compensate for the voltage difference. Taps are usually available in either 2.5% or 5% increments above and below normal. Let's look at a standard dry-type distribution transformer with two 2.5% taps above and two 2.5% taps below normal. The primary wiring diagram looks like this. Let's assume that the rated voltage is 480 volts. 2.5% of 480 would be 12 volts, making the above normal taps available at 492 and 504 volts. To achieve a matching turns ratio for 504 volts, the source lines are connected to H1 and H5, and for 492 volts, the lines are connected to H1 and H4. Normal 480-volt connections are to H1 and H3. Now, below normal taps are available at 468 and 456 volts. To use the 468-volt tap connection, the line must be connected to H2 and H4. The last below normal tap would be 456 volts, and the lines would be connected to H2 and H3. All of these connections will ensure that the secondary voltage will remain constant. Time for a slight pause to reflect on the terms 3 and 4 wire configurations. Let's spend some time understanding this in more detail. 3-wire voltage sources are usually delta configurations as seen in this diagram. Let's assume this is rated at 480 volts. In this case, the voltage across phase A and B will be single-phase 480 volts as well as the voltage across B and C and A and C. These would also be 480 volts single-phase. While the voltage across A, B, and C would be equal to 480 volts 3-phase. 4-wire voltage sources are usually Y configurations as seen here. This example assumes a 480 Y277-volt 4-wire source. We know that the neutral voltage is 277 because the formula seen here states that the line voltage divided by the square root of 3 determines the neutral voltage. In our case, 480 volts divided by the square root of 3 calculate the 277 volts. This formula is the same for any voltage. To further visualize this effect, let's look at the diagram further. As with the delta configuration, any phase to phase such as A and B, B and C, and A and C equate to 480 volts single phase and A, B, and C equals 480 volts 3-phase. A voltage of 277 volts is achieved by connecting any phase to neutral. Phase A to neutral, phase B to neutral, or phase C to neutral becomes 277 volts single phase. This voltage is very popular for industrial lighting in factories. Next, in the distribution substation you will find voltage regulators. Now, why are they needed? We previously mentioned the transformer and the taps. The taps help adjust the voltage output of the transformer. This fluctuation in voltage can create equipment performance issues down the distribution line. Power distribution voltage regulators maintain power distribution system voltages within a defined range. Electrical products and equipment are typically designed to operate within a limited voltage band. Problems that can occur include damaged electronics, inefficient operation of motors, dim light bulbs, and a myriad of other issues. Heavy electrical loads and long distribution lines drag down system voltages. Voltage regulators enable utilities to maintain voltage levels within acceptable ranges, giving customers the assurance that electrical equipment will operate properly. Voltage regulators are supplied as single-phase and provide a 32-step tap changer, which in turn allows for a total regulation of plus or minus 10% of system voltage. Steps are displayed on an indicator shown here. This tap changer can automatically sense the voltage and adjust, or it can be manually adjusted with switches on the regulator or with a remote operator station. The tap changer is mounted internally and rotates to the proper point to provide the required output voltage. The control box seen here can contain advanced electronic features that can connect to a SCADA system that remotely monitors the voltage and can send a signal to have the tap changer move to provide the acceptable voltage level. One last point about the voltage regulator is that it only needs to be sized for 10% of the required load. Now that we have examined all the components in a distribution substation, let's take another look at our diagram. The power then goes out through distribution lines. Distribution lines are used to carry electrical power from the substation to factories and businesses that need power. These can be overhead or underground. Overhead lines are less expensive but more susceptible to fault conditions from tree and animal contact, vehicle accidents, lightning, and wind. This is illustrated with the green lines of this image and highlighted here. If we zoom in on that portion, you will see that it can be broken down into three types of utilization voltages for customers. A sub-transmission customer receives service with voltages of 26 kV to 69 kV. These are very large industrial or co-op type utilities. A primary customer requires between 13 kV and 4 kV to operate machines in a small industrial plant. Lastly, there is a secondary customer receiving voltages of 120 and 240 volts. These are residential or small commercial facilities. As we finish our discussion on distribution substations, we should touch on three other pieces of equipment you might encounter: power correction capacitors, reclosers, and fuse cutouts. By installing capacitor banks strategically along the transmission and distribution lines, utilities can reduce the amount of reactive power that needs to be supplied by the system, leading to a more efficient use of electrical power. This results in several advantages, including reduced energy losses, increased transmission capacity, and improved voltage regulation. Ultimately, capacitor banks contribute to the overall reliability and performance of the transmission system. These are supplied in outdoor cabinets or in overhead racks as seen here. Reclosers are equipped with smart or overload sensors and electronics specially designed to protect the power grid and the customer, automatically isolating the error and recovering if the defect has been corrected. The recloser senses when trouble occurs and automatically shuts off the power. A fraction of a second later, the recloser turns the power back on, but if the trouble is still present, it shuts it off again. These could be because cables momentarily touching, a short lightning strike, or surges causing a spark. If the fault condition is still present after 3 attempts, the recloser is programmed to consider the problem permanent and it remains off. These could be the result of a lightning strike, fallen tree branches, or motor vehicle crashes. A power company crew must then repair the problem on the line and reset the recloser to restore power. These are available in single phase, providing independent protection on each phase, or 3-phase protection. In electrical distribution, fuse cutouts are a combination of a fuse and a switch, used primarily in overhead feeder lines and taps to protect distribution transformers from current surges and overloads. An overcurrent caused by a fault in the transformer or customer circuit will cause the fuse to melt, disconnecting the transformer from the line. A cutout consists of three major components. First, the cutout body is an open, C-shaped frame that supports the fuse holder and a ribbed porcelain or polymer insulator that electrically isolates the conductive portions of the assembly from the support to which the insulator is fastened. Second, the fuse holder, also called the fuse tube or door, is an insulating tube which contains the replaceable fuse element. When the contained fuse melts, or blows, the fuse holder drops out of the upper contact, breaking the circuit, and hangs from a hinge on its lower end. The third component, the fuse element, or fuse link, is the replaceable portion of the assembly that melts and breaks the circuit when the electric current through it exceeds its rated current value. Fuse cutouts are hook-stick operated to open or close. Here you see a technician tending to the fuse cutout with the hook stick. The cutouts are available in various ratings depending on the operating voltage. As the utility distributes power down the line and as it enters into a building, it is termed service entrance. Service entrance is the point at which the electrical power from the utility enters a building. Only one service entrance point is allowed. Load centers or panel boards must contain a main breaker to comply with service entrance requirements, unless they qualify for the NEC exception using the 6 disconnect rule. The National Electrical Code discusses service entrance equipment in Article 230. Load centers used as service equipment must be listed and labeled as such. These feeds can come from an overhead transformer as seen from these two photos, or can come from an underground pad-mounted or compartmental transformer depicted in this image. Coming up we see how the power gets distributed throughout the building. Every residential, commercial, and industrial building has a power distribution system that takes power from the utility at the service entrance and distributes it to where it is needed to run equipment and machinery. Let's spend some time examining the ways this takes place. In this image you can see power distributed from the utility to an outdoor power center. From there, busway is used to enter the building to feed the main switchgear. Depending on the size of the plant, there could be one or more indoor power centers. Here is an image of a typical indoor power center. You will notice that cable and conduits instead of busway helps to distribute power. Power centers may also be double-ended as seen here. These accept two different feeds and have a tie breaker that allows for supply power flow to feeders in the event one source goes down. These are also referred to using the term main tie main. Here is what it would look like on a single line diagram. Usually, there is an interlock system used when the tie breaker is closed. Back to our original image. From that point power travels to distribution panels, and/or motor control centers throughout the plant. It would also supply power for motor control centers, transformers, safety switches and enclosed breakers. Even down to supplying power for office lighting and power receptacles. It might be helpful to see how some of the terms we learned are applied with this typical industrial power system diagram. Segments of this diagram can be broken down into service entrance, as previously mentioned, to feeders and branch circuits. Now let's look at the flow or distribution of power. The utility feed comes into the service entrance equipment. It is distributed to a main feed which in turn feeds a motor control center. Later we will examine a single line diagram depicting the equipment in a motor control center or MCC. A main switchboard feeds a power panel board plus some other loads. The power panel board also feeds a lighting panel board for lighting and receptacles. It has another feeder that feeds a distribution panel for some specific equipment. Industrial plant power varies from industry to industry, but this provides a general breakdown of how power is distributed. Hi, we hope you enjoyed the sample video of our online e-learning module. This clip is from one of our many available modules. We are always working on new modules just like this switch rack course. Here is the current list of developed lessons. Did you know that 16 of our courses carry 22 NETA CTD credits, and we have courses suitable for Pennsylvania and Delaware CEU credit? New modules are being constantly added, so check back with us on our website trainingtogo.net. Let our Training to Go programs train your people while you run your business.